Okay, so I want to quickly show you how to calculate the moment of inertia of something more complicated than a thin rod, something like a spinning disc, because it's really cool. It teaches you a few techniques that as you get more and more comfortable with calculus and integrals, you'll be able to employ a little more freely as the year goes on. Okay, so remember, I want to get the moment of inertia of this thing spinning around. Ooh, what's happened to my focus? There we go. Spinning around this point P over here, which is like an axis through its center that way. So it's spinning, you can see my arrows, and I want to get its moment of inertia through the center. Let's say it has a mass m, a radius r, and since I know my strategy for calculating this is going to be to take a tiny little piece of mass, I need to say, like in this little square, in this little area, how much area is that? What's the mass of that little strip? And then I need to add it up all over, weighted by how far away it is from the rotation axis. To do that, I need remember we were doing the center of mass of a variable density rod. We needed that linear density. We needed to be able to take that and look at what that linear density, how it varied along the rod. Similarly, even though this is a uniform disk, we need to be able to represent like its density. And since it's sort of we're not thinking about it as a volume, but more as a disk, what we normally use to represent that is sigma. And that's going to be the mass divided by the area, which is pi r squared. So that's the mass per unit area. So that's kilograms per meter. So that's my disk. Sometimes you're given that directly. Sometimes you're given the mass on the total radius, and you could figure it out. But so if I take sigma and multiply by any portion of area, it'll give me the mass of that area. So now I'm going to draw a little mass over here, a little dm. And that's one way I can do this. And I can say that dm is a distance r from the center, and I can figure out how much mass dm has and then add it up over the whole thing. But there's a slightly more clever way to do that, and that's by noticing the symmetry here. This is radially symmetric. So what that means is that really, no one told me my dm's had to be squared. They just have to be tiny, infinitesimal, that I could sort of move them over and like sort of extend them out over the whole surface of the object. So I'm going to make my dm a tiny little ring of width dr. That's super tiny. And it's so tiny and so thin that I can basically approximate the area of this little ring that I'm going to call it, I can call it dA if I really wanted to, and that's what I would probably call it, but I'm going to call it the tiny little area over there is basically going to be 2 pi r, which is a ring at that distance r, then times dr, which is the tiny thickness. So I've basically done essentially like a little, width times length, and I've gotten a tiny little rectangle. If you picture that being so small, if I cut it, I could stretch it out to be a rectangle. That's my little area. Now if I want to get my dm of that ring, it's going to be sigma times 2 pi r dr. That's the mass. It's the mass density times the area. Kilograms per meter squared times meters squared. Now I can come and do my integral. I is going to be the integral over that whole object, whatever variable I'm integrating for. I'm going to try to represent my bounds of integration according to what I'm integrating for. And I want to do r squared dm. And I would do that like over the whole mass of the object. But instead I'm going to write it this way. Integral of r squared, because I can't integrate r against dm, those are two different variables, but dm I have right here in terms of r and dr. That's going to be sigma 2 pi r dr. And now I can do that over the whole area, means stretching r from 0 to r, because since these are rings, the rings are just going to start tiny and get bigger and bigger and bigger, and I'll cover the whole area. So the I is going to be, I'm going to pull out all the constants now. 2 pi and sigma are constants. 2 pi sigma, and for sigma I can put that in if I wanted to, but 2 pi sigma, the integral from 0 to r of r cubed, because there's two of them, dr. And that's equal to 2 pi sigma r to the fourth over 4. And since I have bounded integrals, I don't need a constant, I just evaluate that from 0 to r. So my moment of inertia is 2 pi. Now for sigma, I'm going to actually put in what it is. M over pi r squared. And then r to the fourth over 4. And let's simplify. So r squared makes this r squared. Pi cancels pi. And 2 cancels 4. And I get 1/2 mr squared, which is the known value for the moment of inertia around a center of a spinning disk. So that's cool. Let's say I wanted to spin it around this random point that was like some distance d away. So I like stuck a thing in here and I spun it in this lopsided way. My new I would be my old I, 1/2 mr squared plus md squared, where d is the distance to that new parallel axis. Then if I was spinning it at a rotation omega, I would do my kinetic energy as 1/2 I omega squared. There you have it. I hope that was fun. It's actually really fun to try different shapes. So if you want a little challenge, pick like one of the rings or the rods in there and see if you could replicate through that process the center of mass of one of the things. All right, see you later. Bye.